Okay, this is chapter 3. This week we will cover the last topic, which is the frequency response of the BJT amplifier. Okay, this is the slide show you what we have done so far. So in the second week of the chapter BJT, we have discussed on how we can do the DC analysis. So the objective of the DC analysis is to determine the DC operating point of the BJT. So we want to make sure that the BJT is at the suitable operating point. So in our course, we want to use the BJT as in the amplifier circuit. So BJT need to be in active operating region. So the Q point here is the coordinate of the collector current value and the collector emitter voltage value. So from these two values, we can determine whether the BJT is in the active operating region or not. Okay, and then after that, if the BJT is at the active operating region, so means that BJT can operate as a amplifier. So next we need to do the AC analysis to analyze the input impedance, output impedance, and the AC gain. So this is the gain of that relate to the how much the output signal will being amplified by the BJT amplifier circuit. Okay, for this AC analysis, we consider several consideration when we drawing the equivalent circuit or when we do the AC analysis. So for example, we replace the capacitor with the short circuit. So this consideration is actually the consideration where we consideration for the BJT amplifier operate at a mid-band mid-band region. Okay, so the term of mid-band is the frequency actually refer to the frequency range. The mid-band refer to the frequency range where the amplifier has high gain and stable gain. Okay, so in the previous week analysis, the calculated AC gain is at the frequency range where the amplifier has high and stable gain. But however, if the frequency of the amplifier or the frequency of the signal decrease toward the low frequency region, so what will happen to the AC gain? The AC gain will start to decrease. Okay, so we have here the mid band, when the frequency at the lower frequency, the gain decrease. Okay, if the frequency increase from the mid band towards the high frequency region, the gain also decrease. So in this week, we will discuss on the low frequency region and high frequency region. Okay, the frequency response of amplifier refer to the frequency range in which the amplifier will operate with negligible effect from capacitor and capacitance in device. So this is what I have said just now. When we analyze the AC performance of the BJT amplifier, we assume the capacitor to behave as a short circuit. Okay, so actually we ignore the effect of the capacitor. Okay, in actual case, the capacitor will affect the performance of the circuit because it will have a certain value of the impedance. But here, in a certain frequency range, this capacitor can be ignored. So this range of frequency is called the midband. But however, at the low frequency, the capacitor cannot be ignored. So we have in the BJT circuit, we have coupling and bypass capacitor. But this capacitor will affect the performance of the BJT For example, in specifically on the BJT, on the amplifier gain at low frequency. Okay. On the other hand, at the high frequency operation, what will happen? There will be a effect from the what we call stray capacitance. And stray capacitance is actually the capacitance, a very small capacitance associated with the active device, lower the active device, or we call it a parasitic capacitance. The stray capacitance or parasitic capacitance is actually the capacitance that form during the fabrication of the BJT at the junction of the PN junction, at the PN junction inside the BJT. So this stray capacitance actually is very difficult for us to control the value unless we control it, unless we modify the fabrication process. Okay, and then another consideration is the cascading amplifier limit the gain at high and low frequency. What is cascading amplifier? Cascading means that in certain case, for example, we need to have a very high voltage gain. So maybe one BJT amplifier is not enough. So we need to have two amplifier connected in series. So we have, this is amplifier 1, and then amplifier 1, the output of amplifier 1 will be the input of amplifier 2. Okay. So the input of amplifier 1, let's say this is a signal, this is the input, and then the output for amplifier 2 is our overall output. So by having these two amplifiers connected in series, we will have much higher amplification effect. So this connection where the output of the amplifier 1 become the input of amplifier 2 is called cascading. Okay, this is cascading. So this is cascading amplifier. So this type of connection will also limit the gain at high and low frequency. Okay, the statement in the previous slide can be shown from in the circuit. So this is what happened at low frequency. So at mid frequency, we will replace the CS, CC, and CE with the short circuit. So we will not they will not appear in the mid band equivalent circuit. But at low frequency, CS, CC, and CE cannot be replaced, cannot be ignored, or cannot be replaced with the short circuit. So we need to consider this capacitance. Okay, this is at low frequency. And then at the high frequency, so what happened? The CS, CC, and CE, okay, so there is no CS, CC, and CE because it can be considered as a short circuit. But however, we can see the effect of what we call it a parasitic capacitance. Okay, parasitic capacitance is appear or exists between the junction or between the terminal of the BJT. So we have here, this is CBC is the stray capacitance between the base and collector, and then between collector and emitter we have CCE, and then we have CBE. So between the terminal of the BJT we have a stray capacitance or parasitic capacitance. Okay. Beside of this the junction capacitance inside the BJT, we also have the stray capacitance or parasitic capacitance in the wiring or in the electrical connection of the circuit. So we have this wiring at the input, CWI, and CWO is wiring at the output. So this stray capacitance and parasitic capacitance will appear at high frequency. Okay. And then the difference between the stray capacitance and the capacitor that we added as the coupling and bypass is the value. The parasitic capacitance value is very small compared to the coupling and bypass capacitor. Okay. In general, parasitic capacitance can be in value of picofarad. So, and then coupling and bypass capacitor in microfarad. So, pico is 10. Pico is 1. Nano is 10 power of minus 9. So, pico is minus 12. So, and then microfarad is 10 power of minus 6. So, this is you have around 6 order different between the parasitic capacitance and bypass capacitance. Okay, so why this capacitor affect the circuit? Okay, you can see you can analyze in terms of the reactance or the impedance of the capacitor. So for example, we have this in this table we have two values, 1 microfarad. So microfarad represent this the coupling and the bypass. Coupling and the bypass. And then we also have another value which is very small, 1 picofarad. So 1 picofarad is the parasitic capacitance. So if we calculate the impedance, or we call it reactance, impedance at different frequency. For example, at low frequency, okay, at low frequency around 10 Hz. So at low frequency around 10 Hz, the impedance of the coupling and bypass capacitor is around kilo ohm. And then the parasitic capacitor is around 100 mega ohm. So because this parasitic capacitance is very high, so we can assume we can ignore it and then replace it with open circuit because very high impedance. So that's why the parasitic capacitance is not appear in the at low frequency. However, at low frequency, this is quite large. This is comparable value for the coupling and bypass capacitor will have the impedance that is comparable with the other other resistance inside the biasing circuit. Okay, if you see the at the 10 kHz, what happened at the 10 kHz? At 10 kHz, the coupling bypass capacitor, the impedance is 15 ohm. So it's quite low. So this is can consider as short circuit. And then this one is also quite high. It's open circuit. So this is the point. This is the frequency where we call it a mid band. Okay, so this is the mid band frequency where we can ignore the capacitor, coupling and bypass capacitor, replace them with the short circuit, and then we can ignore the parasitic capacitance by replace them with the open circuit. So again, at the low frequency, we cannot ignore the bypass because it has high, is non-negligible value of the impedance. So and then at the high frequency, what happened? The coupling and bypass can be ignored because very low impedance. However, the parasitic capacitance will have will have a moderate value of impedance. So this we cannot assume as the open circuit. So it will appear inside the circuit. Okay. So we discussed about the mid band, low frequency and high frequency. So and then the effect of the frequency to the gain of the amplifier. So actually we have a plot. We call it Bode plot. So the Bode plot indicate the frequency response of amplifier. So we have the y-axis is the gain, in the dB, usually we use a dB unit, the gain, and then x-axis is the frequency. So from the Bode plot, we can see the change of the gain with respect to the frequency. Okay. You may notice that at the middle region, we have a quite stable and the highest gain. So we have, this is the highest gain. So this is what we call a mid band or mid frequency. Okay. So in previous week, we are calculating this value, the value at the mid band. Okay, and then the mid-range frequency of amplifier is called bandwidth. So bandwidth is defined by the lower and upper cutoff frequency. So the bandwidth is the frequency range where the device or where the amplifier can optimally operate as the amplifier. Okay, so how we can determine the value of bandwidth is by taking the what we call it lower cutoff frequency, and then we consider the high cutoff frequency. So high cutoff frequency minus low cutoff frequency, we will have the bandwidth. So this is FH, high cutoff frequency. This is FL, low cutoff frequency. So FH minus FL. So this will be the bandwidth. Okay. Okay. So what is cutoff frequency? Cutoff frequency is where the gain, the frequency where the gain start to decrease. So at low frequency, and the same goes at the high frequency. Okay, so this is the borderline where we have the mid band and then we have the low frequency, or mid band with the high frequency. So how we define this borderline is using this consideration. So okay, sorry. Okay, so how we define the cutoff frequency is by this condition. So usually we consider this minus 3 dB. So the cutoff frequency is where the frequency where the gain decrease minus 3 dB. For example, if the AV mid, so AV mid is the gain at the mid band. Okay, if the AV mid is 30 dB, so we need to find the frequency where the AV become 27 dB. So we find the frequency where the voltage gain become 27 dB, and then we can have the FL as well as FH. Okay, so you may notice that the x-axis in the Bode plot is not a normal linear scale. So for the x-axis, we use x-axis for the good lot, use the log scale. Use a log scale. So the use of log scale can significantly expand the range of variation of a particular variable on a graph. So if you use the linear scale, let's say you have a wide range of data, the data value. So for example, you have 1 Hz, you have 10 Hz, you have you have 1 Hz, and then you have 10 Hz, you also have 1000 Hz, you have 50,000. So if you plot it using the linear scale, so you need to determine the interval of the scale. For example, you want to plot, you want to have this, if you use this is 100, 200, 300, 400. This is a linear scale. So if you use this type of linear scale, so you need to have a very long x-axis. But if you use the log scale, so you can compress this wide range of the frequency value within one graph, a very nice one graph. So this is why we use the semi-log graph. So the semi here means that because one axis is log axis, another axis is linear scale. So for the AV, for the gain of y-axis, we will use the linear scale. Okay, so this is the log scale. So log scale, we have the term what we call it one cycle. So if the linear scale, one cycle, for example, in this example, the one cycle is consists of 100. So we have one cycle 100, second cycle, after one cycle 100 become 200. After two cycle 100 become 300. So this is a linear scale. But for the one cycle, for this log scale, one cycle is referring to the changes of tenfold. So what is tenfold? For example, we start here, so this is 1. After one cycle, it will become 10. Okay, it will become 10. Then after another cycle, it will become 100. Okay, so this is how you put the value in the log scale. So here will become, this is not 2, become 20, 30, 40, 50, 60, 70, 80, 90. Okay, become 100. So and then after this next cycle will become 200 to 300, 400, and then so on until 1000.